Imagine a genius who saw beyond what was visible, whose mind revolutionized not only science but also our daily lives. This is James Clerk Maxwell, the man who transformed abstract concepts into practical foundations that shaped modern technology. From his early discoveries in Edinburgh to the formulation of the equations that unified electricity and magnetism, Maxwell laid the groundwork for innovations we see today in smartphones, wireless networks, and global communication systems. His ideas not only influenced scientific giants like Einstein, but also enabled the development of the electronic devices we use every day. In this narrative, get ready to embark on a journey that connects a passion for knowledge with a technological revolution, and discover how Maxwell's vision continues to transform the world around us. In the heart of Edinburgh, Scotland, on June 13, 1831, James Clerk Maxwell was born into a world on the brink of scientific revolution. His family, though of noble descent, led a modest and intellectual life. His father, John Clerk Maxwell, was a lawyer with an affinity for mechanics and mathematics, while his mother, Frances Kay, nurtured his early education with great care. From an early age, young James displayed an insatiable curiosity, an intellect far beyond his years. By the age of 3, Maxwell's fascination with patterns and structures was evident. He would tirelessly explore the countryside around Glenlair, the family estate, observing natural phenomena with childlike wonder. His mother, recognizing his potential, took charge of his education, guiding him through arithmetic and scripture. However, tragedy struck when she passed away from cancer, when he was just 8. This loss left a profound mark on Maxwell, and his father, though devoted, struggled to fill the void she left in his education. At 10, Maxwell was sent to Edinburgh Academy, where his brilliance began to manifest fully. Though initially ridiculed for his rural accent and eccentric demeanor, he soon earned the respect of his peers with his astounding memory and inventive problem-solving abilities. At just 14, he wrote his first scientific paper on mathematical curves, a work so advanced that it had to be presented to the Royal Society of Edinburgh by a professor, as Maxwell was deemed too young to do so himself. Recognizing his extraordinary aptitude, Maxwell's father encouraged him to pursue higher education. At 16, he enrolled at the University of Edinburgh, where he immersed himself in mathematics and natural philosophy. Under the mentorship of luminaries such as Sir William Hamilton, he refined his skills in analytical reasoning. Yet Maxwell remained an independent thinker, challenging existing ideas and forging new paths in scientific inquiry. With his foundational years shaping a mind destined for greatness, Maxwell's journey was just beginning. The halls of Cambridge awaited, where he would ascend to the echelons of theoretical physics, setting the stage for a revolution in science. If you're enjoying the story of James Clerk Maxwell and his incredible journey in the world of science, don't forget to like this video and subscribe to the channel. It helps us continue bringing inspiring stories of great minds that changed the world. Now let's dive back into his journey and groundbreaking discoveries. In 1850, at the age of 18, James Clerk Maxwell left Edinburgh for the University of Cambridge, a move that would solidify his place among the brightest minds of his time. He entered Peterhouse College but soon transferred to Trinity College, where he found an intellectually stimulating environment that matched his insatiable curiosity. Cambridge was the epicenter of mathematical physics, and Maxwell thrived under the mentorship of some of the greatest scholars of the era. Among his influences was William Hopkins, known for training the best mathematicians of the time, and George Stokes, whose work on fluid dynamics and optics would later intertwine with Maxwell's studies. The rigorous mathematical training at Cambridge allowed Maxwell to refine his analytical abilities, and by 1854, he graduated as second wrangler, one of the top students in his class. He was also awarded the prestigious Smith's Prize for his outstanding work in applied mathematics. During his time at Cambridge, Maxwell delved into a variety of scientific inquiries. One of his earliest major contributions was in the study of the stability of Saturn's rings, a problem that had puzzled astronomers for centuries. By applying mathematical analysis, Maxwell demonstrated that the rings could not be solid or liquid, but must consist of countless small particles orbiting Saturn, an insight that was later confirmed by space probes over a century later. Beyond celestial mechanics, Maxwell turned his attention to the study of elasticity and geometry. He was deeply fascinated by the behavior of stress and strain in materials, which would later influence his approach to electromagnetism. His ability to blend pure mathematics with physical intuition set him apart from his contemporaries, establishing him as a thinker who sought unity in scientific principles. By 1856, Maxwell secured a professorship at Marischal College in Aberdeen, marking the beginning of his teaching career. Though still in his 20s, he was already laying the foundation for theories that would revolutionize physics. His work was about to take a dramatic turn toward an area that would define his legacy: electromagnetism. By the late 1850s, James Clerk Maxwell's mind had begun gravitating toward one of the most intriguing mysteries of his time: electromagnetism. The works of Michael Faraday, who had experimentally demonstrated the presence of electric and magnetic fields, fascinated Maxwell. Faraday, a self-taught scientist, had introduced the concept of lines of force to explain how electric and magnetic forces extended through space. However, Faraday lacked the mathematical framework to formalize his discoveries. Maxwell saw an opportunity to bridge the gap between theory and experiment. At Marischal College in Aberdeen, Maxwell began constructing a rigorous mathematical description of electromagnetic phenomena. He sought to translate Faraday's intuitive concepts into equations, giving them a concrete analytical structure. However, the scientific community of the time was not entirely receptive to Faraday's field-based ideas, as most physicists still preferred the more tangible concept of electric and magnetic forces acting at a distance. In 1860, Maxwell moved to King's College London, where he continued refining his ideas. It was here that he conducted one of his most remarkable experimental studies, his work on color perception and optics, which contributed to the development of early color photography. However, his primary focus remained electromagnetism. Maxwell approached the problem by considering the nature of electric and magnetic fields as interconnected entities. He proposed that changes in an electric field could induce a magnetic field and vice versa. This concept was revolutionary, as it suggested that electromagnetic fields could propagate through space as waves. He began formulating a set of mathematical equations to describe these relationships, but the work was far from complete. Despite the challenges, Maxwell's confidence grew. He had glimpsed a fundamental truth about nature, a hidden symmetry in the forces of electricity and magnetism. He knew that if he could fully develop these ideas, they might lead to profound scientific advancements. The next step was to find a way to unify these concepts into a coherent framework, one that would forever change our understanding of the physical world. By the mid-1860s, James Clerk Maxwell was on the brink of a groundbreaking discovery. He had spent years refining his mathematical formulation of electromagnetism, inspired by Michael Faraday's experimental insights. At King's College London, he finally consolidated his findings into a set of equations that would become one of the most profound achievements in physics. Maxwell's equations, as they would later be called, described how electric and magnetic fields interact and propagate through space. His mathematical framework consisted of 4 fundamental equations that unified electricity and magnetism into a single theory. These equations revealed a crucial insight. Electromagnetic fields could travel through space as self-sustaining waves. What's more, when Maxwell calculated the speed at which these waves would move, the result was strikingly close to the known speed of light. This discovery led him to propose an audacious idea. Light itself was an electromagnetic wave. For centuries, physicists had debated the nature of light, with theories ranging from particle models to wave-based descriptions. Maxwell's work settled the matter, demonstrating that visible light as well as infrared and ultraviolet radiation were all part of a continuous electromagnetic spectrum. However, acceptance of his theory was not immediate. Many physicists of the time found his mathematical approach too abstract, preferring experimental verification over theoretical predictions. Furthermore, the existence of electromagnetic waves had yet to be observed directly. It would take another 2 decades before Heinrich Hertz, building upon Maxwell's work, successfully detected these waves in a laboratory setting, providing definitive proof of their existence. Despite initial skepticism, Maxwell's equations laid the foundation for a new era in physics. They provided the theoretical backbone for the development of radio waves, wireless communication, and countless modern technologies. His work not only unified electricity and magnetism, but also hinted at the deep underlying connections within nature, connections that future scientists would strive to uncover. Maxwell had rewritten the laws of physics, but his influence would not stop there. His vision of unification would inspire the great scientific revolutions of the 20th century, shaping the theories of relativity and quantum mechanics in ways he could scarcely have imagined. James Clerk Maxwell's equations were more than a mathematical triumph. They were the key to unlocking a new technological era. Though not immediately embraced, his work on electromagnetism would go on to shape the modern world in ways he never lived to see. By mathematically proving the existence of electromagnetic waves, Maxwell laid the foundation for technologies that would transform communication. Radio waves, microwaves, and later television and radar systems were all direct applications of his discoveries. In the late 19th century, Heinrich Hertz experimentally confirmed the existence of these waves, and soon after, Guglielmo Marconi developed the first wireless telegraphy systems. The radio revolution had begun, all stemming from Maxwell's theoretical insights decades earlier. Beyond telecommunications, Maxwell's equations played a crucial role in shaping modern electrical engineering. His work provided the principles governing electrical circuits, transformers, and electromagnetic radiation, forming the basis for power generation and distribution. The alternating current systems pioneered by Nikola Tesla and the development of radio transmission by Marconi and others were deeply rooted in Maxwell's vision. Perhaps the most profound consequence of his work was its influence on Albert Einstein. In 1905, Einstein's formulation of special relativity was built upon Maxwell's realization that the speed of light was a fundamental constant of nature. Maxwell's equations were inherently compatible with relativity, suggesting that space and time were deeply intertwined, an idea that paved the way for the most revolutionary advances in physics. Furthermore, Maxwell's theories hinted at a broader unification of forces, a concept that still drives modern physics. His vision of connecting electricity and magnetism inspired later attempts to unify the fundamental interactions of nature, leading to developments in quantum electrodynamics and the ongoing search for a grand unified theory. Maxwell's legacy was growing, and his work was no longer confined to the pages of scientific journals. It was now embedded in the very fabric of society. His insights had illuminated the invisible forces governing the universe, and the world was only beginning to grasp their full significance. While Maxwell's groundbreaking work on electromagnetism is often seen as his greatest achievement, his contributions to thermodynamics and statistical physics were equally profound. In the mid-19th century, physicists were striving to understand the behavior of gases, and Maxwell was among the pioneers who transformed this field by introducing statistical methods to describe the microscopic motion of particles. One of his most significant contributions was the Maxwell-Boltzmann distribution, developed in collaboration with Ludwig Boltzmann. This statistical law describes how gas molecules are distributed according to their speeds, demonstrating that the velocities of individual particles in a gas vary based on probability. Before Maxwell, scientists typically treated gases as continuous substances. His work revealed that their properties could be understood by analyzing the motion of billions of tiny particles. His insights into kinetic theory provided a deeper understanding of temperature, pressure, and energy exchange. Maxwell's work helped confirm that temperature was not a fundamental property of matter, but rather a measure of the average kinetic energy of particles in motion. This concept revolutionized thermodynamics and laid the groundwork for the development of statistical mechanics. Another fascinating idea that emerged from his work was Maxwell's demon, a thought experiment that challenged the second law of thermodynamics. He imagined a tiny, intelligent being capable of sorting fast and slow-moving gas molecules, seemingly reducing entropy and violating the fundamental principle that entropy always increases. While the paradox sparked much debate, Later studies showed that even Maxwell's demon could not escape thermodynamic laws. Nonetheless, the concept remains a cornerstone in discussions about entropy, information theory, and the limits of physics. Maxwell's statistical approach paved the way for the quantum revolution of the 20th century. His work influenced pioneers like Einstein, who applied similar probabilistic methods to explain Brownian motion and light's particle-like behavior. Without Maxwell's insights, modern physics as we know it might have taken a very different path. Even as he continued to revolutionize multiple fields, Maxwell remained modest, always focusing on uncovering the deep, hidden patterns of nature. But his time was running short. His health was beginning to decline, and he faced the final years of his remarkable life. As the 1870s progressed, James Clerk Maxwell's reputation as one of the greatest scientific minds of his time was solidified. In 1871, he accepted the prestigious position of the first Cavendish Professor of Physics at the University of Cambridge. His appointment marked a return to the institution that had shaped his academic career, and it was here that he would leave his final mark on the scientific world. One of his greatest undertakings during this period was the establishment of the Cavendish Laboratory, a world-class center for experimental physics. Maxwell played a key role in designing the facility and setting its research agenda, ensuring that future generations of physicists would have the tools and resources to advance scientific knowledge. Under his guidance, the laboratory became a birthplace for revolutionary discoveries, including J.J. Thomson's eventual identification of the electron. Despite his growing administrative responsibilities, Maxwell remained deeply engaged in research. He revisited his earlier work on color perception and optics, conducting experiments that laid the foundation for modern color photography. His insights into human vision, particularly the way the eye perceives red, green, and blue light, were later used in television and digital imaging technologies. As his career neared its end, Maxwell also turned his attention to the philosophical implications of science. Unlike many of his contemporaries, he saw no conflict between scientific inquiry and religious faith. He often spoke of the harmony between mathematics and the natural world, believing that the laws of physics revealed a deeper, underlying order to the universe. He saw his work not just as a collection of formulas, but as a window into the very structure of reality. However, despite his towering intellect and tireless dedication to science, Maxwell's health was in decline. By 1877, he began experiencing intense abdominal pain, yet he continued his work undeterred. Though his body weakened, his mind remained sharp, constantly pondering new scientific problems. He had spent his life unraveling the mysteries of nature, but fate had already set his final chapter in motion. By the late 1870s, James Clerk Maxwell's health had begun to deteriorate. At first, he dismissed the symptoms, fatigue, stomach pain, and weight loss, as mere signs of overwork. But the discomfort grew more severe, and by 1877, it became clear that something was gravely wrong. The same illness that had claimed his mother when he was just 8 years old had now come for him: abdominal cancer. Despite his suffering, Maxwell remained dedicated to his work. He continued to lecture at Cambridge, guiding young physicists at the Cavendish Laboratory, and refining his scientific theories. Colleagues noticed his declining strength, but he rarely spoke of his pain, refusing to let illness hinder his intellectual pursuits. His resilience was remarkable, yet his condition worsened rapidly. By mid-1879, Maxwell's situation had become dire. With his devoted wife Catherine by his side, he retreated to Glenlair, his family estate in Scotland, seeking rest. In the familiar countryside he had loved since childhood, friends and students wrote to him, offering their support and gratitude, but Maxwell was growing too weak to respond. Though his body was failing, his mind remained sharp. In his final conversations, he reflected on the interconnectedness of the physical world, the elegance of mathematics, and the mysteries of existence. To those around him, he remained the same humble, thoughtful man, brilliant yet unassuming, always more interested in the pursuit of knowledge than in personal recognition. On November 5, 1879, at the age of 48, James Clerk Maxwell passed away peacefully, The scientific world had lost one of its greatest minds, but his legacy was only beginning. At the time of his death, his groundbreaking contributions to electromagnetism were still not fully appreciated. Yet, in the decades that followed, his work would revolutionize physics, paving the way for technological advancements beyond anything he could have imagined. Maxwell was laid to rest in the small churchyard of Parton, near Glenlair. There was no grand funeral, no public spectacle, just a quiet farewell to a man who had reshaped the scientific world with his genius. But his equations, his insights, and his vision would live on, guiding generations of physicists toward the deepest truths of nature. In the years following James Clerk Maxwell's passing, the true magnitude of his contributions to science became evident. His work, once seen as purely theoretical, laid the foundation for the technological and scientific revolutions of the 20th and 21st centuries. Though his genius was not fully recognized in his lifetime, today he stands alongside Newton and Einstein as one of the greatest physicists in history. The impact of Maxwell's equations extended far beyond the realm of academia. By unifying electricity and magnetism into a single theoretical framework, he had provided the mathematical groundwork for wireless communication, radio waves, and later, television, radar, and satellite technology. Every modern electronic device, from smartphones to GPS systems, owes its existence to the principles Maxwell uncovered. Albert Einstein himself held Maxwell in the highest regard, once stating, "The work of James Clerk Maxwell changed the world forever." Indeed, Maxwell's equations played a crucial role in the development of special relativity. His realization that the speed of light was constant in a vacuum challenged classical physics and inspired Einstein's revolutionary theories about space and time. His contributions also extended into thermodynamics and statistical mechanics, fields that would later influence quantum mechanics. The Maxwell-Boltzmann distribution remains a cornerstone of statistical physics, helping scientists understand the behavior of gases and complex systems. Maxwell's work in color vision even laid the foundation for modern imaging technologies, including photography, television screens, and computer displays. Though Maxwell's name is not as widely known among the public as Einstein's or Newton's, physicists today recognize his immense impact. In his honor, the unit of magnetic flux, the Maxwell MX, was named after him, and his legacy is commemorated through institutions like the Maxwell Institute for Mathematical Sciences. His image also adorns university walls and scientific institutions around the world, a reminder of the man whose equations revealed the hidden symmetries of the universe. James Clerk Maxwell was a visionary, a scientist whose insights connected the physical world in ways few could have imagined. His work continues to shape modern physics, and his quest to understand the fundamental laws of nature remains an inspiration to all who seek knowledge. More than a century after his passing, James Clerk Maxwell's influence remains deeply embedded in the fabric of modern science and technology. His work was not merely a theoretical triumph. It reshaped the world in ways that continue to define daily life, from communication networks to medical imaging and space exploration. Maxwell's equations are now fundamental to physics, governing everything from wireless communication to fiber optics and radio waves. Every time someone makes a phone call, accesses the internet, or watches television, they are witnessing the power of Maxwell's insights. His discoveries made possible the modern electrical grid, radar systems, MRI scans, and even space probes that explore distant galaxies, guided by electromagnetic signals traveling across the cosmos. Beyond practical applications, Maxwell's work set the stage for the great unification efforts in physics. His realization that electricity and magnetism were two aspects of the same force was an early step toward the modern pursuit of a unified field theory, a goal that physicists continue to chase in their quest to understand gravity, electromagnetism, and quantum forces as part of a single framework. Without Maxwell's pioneering vision, Einstein's relativity and quantum mechanics might never have emerged as they did. Even in education, Maxwell's legacy is unmistakable. His approach to physics, melding mathematical rigor with intuitive physical understanding, continues to inspire generations of scientists. Every student of physics learns Maxwell's equations as a fundamental part of their training, and his methods still guide research in electromagnetism, statistical mechanics, and optics. Perhaps most remarkably, Maxwell's story is one of quiet brilliance. Unlike Newton or Einstein, he was never one to seek fame or controversy. Instead, he let his ideas speak for themselves, confident that the beauty of physics lay in uncovering the hidden symmetries of nature. His life is a testament to the power of curiosity, perseverance, and intellectual humility. As we step into an age of quantum technologies, artificial intelligence, and interstellar exploration, Maxwell's discoveries remain as relevant as ever. His vision of a connected, orderly universe continues to inspire those who seek to understand the fundamental forces that shape our reality. James Clerk Maxwell may not have lived to see the full extent of his impact, but his equations endure, etched into the very structure of the universe, guiding humanity toward new frontiers of knowledge.